All right, physics. This is chapter 1, the science of physics, section 3, the language of physics. Okay. Now, our objectives here are to interpret data in tables and graphs and recognize equations that summarize data. Distinguish between conventions for abbreviating units and quantities. Use dimensional analysis to check the validity of equations and perform order of magnitude calculations. Here we go. Tables, graphs, and equations can make data easier to understand. Can doesn't mean it does. Okay. I have looked at graphs that I had no idea how to read. But then again, you get those circle graphs, which are really easy to understand. Just depends on how it's presented to you. For example, here we go. Consider an experiment to test Galileo's hypothesis that all objects fall at the same rate in the absence of air resistance. Well, we already knew what happened with air resistance. Here. This is guy's name is Brian Cox. He's a physicist that likes to do experiments. Now look, the feathers fall slower than the bowling ball. Who didn't see that coming? But that's with air resistance. Okay. Now let's go to without air resistance. All right. What do you think is going to happen? Well, if you said it's just going to fall and keep going at the same rate, you were right. Look at that. They are falling at the same rate. They cleared all the air out of that room. They created a vacuum in there, and then they dropped these two things, and you can see what happens. All right. Let's continue. In the experiment, he was imagining a table tennis ball and a golf ball dropped in a vacuum, and the results recorded as a set of numbers corresponding to the times of the fall and the distance each ball fell. It's a convenient way to organize the data in a table, as shown in the next slide. So let's bring that up. First of all, let me see if I can get the, nope, we're good. All right. Here's the table. Now, let's take a look. In the first fraction of a second, they fall in the same. This is the golf ball. This is the table tennis ball. If you look at it, their numbers are almost identical. As a matter of fact, it's only 1/100th off, which could easily be a rounding error. These two things, in experiment, fell at the same rate, even though your common experience would say that's wrong. Here is a graph of how they fell. Okay. Now, if you notice, the slope here is low, but as you can find, the slope is increasing. That's because the velocity of the object is increasing, okay? When something is dropped, the longer it falls, the faster it's going to fall until you reach terminal velocity. But notice this is not a straight line. This is a curve, okay? Now let's get into that for a moment, okay? If something falls at the same rate constantly, it is simply going to create a straight line as far as time versus distance, okay? However, if something speeds up as it falls, the distance is going to increase over time, okay? Or if something slows down as it falls, then it's going to go like this. But either way, it's not going to be a straight line. So generally, this is what you will deal with. Something is going further as it falls, or if you're going to do it this way, something drops more as it falls. The other option is something called an exponential, which has nothing to do with falling. It has to do with investments and other things. And actually, to do it correctly, I have to make it pass through 1. It would be out here, pass through 1, and then go up. Okay, it's called an exponential. This is exponential. This is a parabola or a quadratic. Parabola. And this is linear. Linear, the rate does not change. Parabola and exponential, the rate changes over time. Okay, back to the slides. Here, physics equations. Physicists use equations to describe measured or predicted relationships between physical quantities. Variables and other specific quantities are going to be abbreviated with letters that are boldfaced and italicized. Whereas units, meters, kilograms, liters, are just regular letters, sometimes called Roman letters, all right? So now that we have those, two tools for evaluating physics equations are dimensional analysis and order of magnitude estimates. We're going to do those together in just a moment. Now, the equation from the drop ball experiment ends up being this. Delta y equals 4.9 times delta t squared. The actual equation is delta y equals 1/2 gt squared, where g is the acceleration due to gravity, but let's not worry about that right now. The delta means change. That means change. Delta y, the change in y, is dependent upon the change in time squared, okay? That is something that's very important to remember. It's going to come up a lot when we do kinematics. The Greek letter delta means change in, and okay, I said all that. This equation allows you to reproduce the graph and make predictions about the change in position for any time, okay? If you don't believe me, let's bring up an online graphing tool. Yeah, Desmos does a really good one. So now watch. I'm going to put in that equation. Y equals 4.9. We're going to call it x squared. And that's what it looks like. Okay. Now, obviously, you wouldn't worry about this half right here. It would just be this half. That's what you would worry about. And so the more time's gone by, the faster it falls, the further it's falling, or the further it has fallen. A couple of things that we haven't looked at yet. Order of magnitude and dimensional analysis. Let's make those very quick. Dimensional analysis is basically this. Let's say you want an acceleration, okay, which is meters per second squared generally. And you're multiplying something that's meters per second times meters per second. Well, is that going to give you meters per second squared? No. Meters squared per second squared. So that don't work. What if I'm doing meters per second times 1 over something that's 1 over seconds, or I'm dividing by time? Well, there you go. That's meters per second squared. So if I do A equals V divided by T, well, that would be, let's get rid of that right there. Oh, this is going to take a moment, isn't it? We'll live. It'll be all right, I promise. Okay, A equals VT, almost done here. Well, velocity is generally meters per second. We can think of it as meters per second. It can be all sorts of other things, but for our purposes, let's do meters per second. So, meters per second divided by seconds is the same thing as meters per second times 1 over second, which is meters per second squared. All right, now let's do a different one. What if you're doing force, which is in newtons? Okay, you're going to learn this later. And a newton is a kilogram times meter per second squared. Okay, what if I'm doing velocity times acceleration? Well, that gives me that. Well, velocity is meters per second, and acceleration is meters per second squared. So that's meters squared per second cubed. Is that? No, that don't work. So maybe I should do kilograms, the mass times, how about mass times velocity? That'd be kilograms times meters per second. Nope, missing a second squared. What gives you second squared? Meters per second squared is acceleration. So kilograms times meter per second squared. There you go. That was not it. That is it. That's dimensional analysis in a nutshell. Now, order of magnitude. Okay, let's say you're going to travel you're going to travel across it. You know what? That one's a little too tough to start with. Let's start with an easy one. You're in Chicago. and you're going to drive to Miami, which is about 1,500 miles, something like that. Well, before we do that, I could be wrong. Before we do that, is the distance going to be on the order of 10 to the 0, which is 1 meter? 10 to the 0 meters? No, too small. Is it going to be like 10 to the first meters, which is 10 to the 1? No, too small. What about 10 to the third meters? Well, 10 to the third is 1,000. And it is about 1,500 miles, I believe. So that's what it would be. It would be on the order of thousands. Okay. Now, if you went 10 to the fourth, 10,000. Nah, that's way too big. Okay. Now let's go back. What about the distance across a helium atom, which is 65 picometers? Well, is that going to be 10 to the first meters? 10 meters? No, way too big. What about 10 to the -2 meters, which is a centimeter? Nah, centimeter is still way too big. All right. This is actually 10 to the -12th meters. A picometer is 10 to the -12th. Okay. What about the length of a dog from here to here, back and forth? Is that about 10 to the first meters, which would be 10 meters? Is that 10 meters? No. It's actually, we go with 10 to the 0 meters, which is just 1 meter. 10 to the 0 is 1. Okay, that's order of magnitude. That's how to tell whether or not an answer you're giving makes sense on at least one level. All right, that is it for this section. We will make sure you do the questions that went along with this, and prepare for your quiz.